The name of the problem this time is the Atwood machine. We will start with a simple version of the problem where we have two masses connected with a string and a pulley, all of which are, as always, assumed massless. We do have friction between the block and the table here, and this is hanging freely. Obviously, we have the force of gravity, which is acting down. Here, we're trying to find two things. Part A, we're trying to find acceleration of the system. B, tension in the string. The tension in the string denote with T. Now, this is a simple problem. Well, we can go two ways about it. One is finding the result by inspection, doing it really quickly without resorting to free body diagrams. This usually works faster. It looks easier, but in harder problems, you may run into trouble. The other method will be drawing the free body diagrams for each of the masses and then trying to solve it. That can take a little more time, but it will work. If you do it correctly, it will work under all conditions. Now, the first thing you can do is, by inspection, you can see that the masses are going to move together. So what we're doing in essence is we're thinking of a coordinate which moves in that direction. Both masses are going to move together because of the string. And also we assume there is motion. And one more thing, the coefficient of friction we're talking about here is the kinetic coefficient of friction because we assume there is motion. We're not asking whether it moves or not. So the first thing to do is then, well, your main equation is F equals ma, force equals mass times acceleration. So our acceleration is obviously going to be in this direction. This mass will go there, and this mass will go towards the right with the same acceleration. So how much force is exerted on the total system? Well, the only force that's going to drive this system is the force of gravity, which is acting on the mass that's hanging down. So that's mg. Now, we also have some force which is counteracting this motion. That will be the force of friction, which acts over here as the frictional force. Now, how do we calculate the frictional force? That's simply the normal force multiplied by the coefficient of friction. The normal force is easy because we know that this is not going into the table. So since this acts with mg down, the normal force is equal and opposite as mg. So the force of friction here is just mu times mg, and it acts to the left because I'm assuming the system will move to the right. So the force, the net force on the system is this driving force minus the friction force. So on the left side, I have mg minus capital Mg times mu equals the mass times the acceleration. Now, the total mass that's moving is the sum of the two masses. So I get m plus m times the acceleration. So just by moving things around, it's easy to see that A equals G times m minus m mu over m plus m. Right. Now that I know the acceleration, how do I find the tension in the rope? Now, I can do it two ways. I need to either go to this mass or that one, and I will have to go to a free body diagram to do this. Now, the simpler one is the one that's hanging down. So if I take that mass and draw a free body diagram, which means I'll just write all the forces that are acting on it. So there is mg acting down. What tries to hold it up is the tension. And that's it. We're going to accelerate down. So the acceleration on it is downwards a. So the equation I'm going to write is, again, F equals ma. Now, the net force on it is mg minus t. Now, I took down as the positive direction because, well, I prefer a positive a, equals little m times a. So the tension in the rope will be what? M times g minus a. So I do know a, so my final answer for the tension in the rope will be, little m times g minus g times m minus m mu over m plus m. This will simplify to mg m plus m minus m plus m mu over m plus m. These cancel. This equals mg m1 plus mu over m plus m. Right. Good. So let's see if our units are right for both answers. In here, I have an acceleration. Well, g is an acceleration. So this part better be unitless. Well, it's mass over mass. It's unitless. I'm fine. Over here, tension is supposed to be a force. Mg is a force. So I'm happy with it. This part is, again, m over m plus m. Makes sense. One thing to look at is whether the position of the coefficient of friction makes sense. If I have more friction, that means it will be held back more than it will be more tension in the rope. So yeah, it does probably make sense. If it was with a minus sign, I would have been really worried. All right, so this is the way to solve it rather quickly by inspection. I'll do it the other way. And this time, we will do free body diagrams for both masses first, and then we'll try to solve the equations. In this case, though, the tension in the string will be in the equations from the start. So if I do a free body diagram for this mass, I have force of friction here. I have mg here. I have acting up, I have the normal force. Since I'm doing it by the rules, I'm not assuming anything from the start. And then over here, I have the tension. And overall, it will be accelerating to the right. So if I write, in this case, I have two equations to write. One is in the vertical direction. Wonderfully, I have no angles, no sines, no cosines. So one equation says, if I take up as the plus direction, says n minus mg equals 0, because the mass does not accelerate in the vertical direction. In the horizontal direction, I have T minus the force of friction equals mass times the acceleration. Equation number 2. Now, from the first equation, I find that the normal force is just mg, which is just to say the table exerts enough force to hold the mass up, pretty much. And one thing you have to supply is that the force of friction is just mu times the normal force, which happens to be then mg times mu. So substituting here, I have T minus mg mu equals mass times acceleration. So this is one equation I get to solve for A and T. The second equation will come from the second mass. So once again, I will take the second mass, mg acting down, tension acting up. In the horizontal direction, well, there are no forces, no acceleration, so I'm just not going to use that equation. So overall acceleration is downwards. So I'm going to say mg minus t equals the mass times the acceleration. OK, so I have two equations, two unknowns. This again means physics is over. The rest is math. So I'm going to solve for A and T. I can. Which one will be better?
You add the equations to get rid of T.
Right. So they're already set up pretty good because I can just add the equations. Yay. Cancel T's. Then I get mg minus mg mu equals m plus m times A. And A equals, again, g little m minus capital M mu over m plus m. Not very surprising. The same answer as last time. Now, well, you don't have to go back and think again. You can use either equation. Now that you know what the acceleration is, you can use either equation to get at t. This time I'll use this for a difference. Not to repeat myself. According to that equation, t equals mg mu plus capital M times A. So it's just mg mu plus capital M times g again, and then this m minus m mu over m plus m. Okay, so we get in what? mg parentheses, we have mu plus m minus capital M mu over m plus m, which is is that right? Seems like it. That cancels that. So I have mg m1 plus mu over m plus m. I think I got the same answer, except I switched the m's places. Doesn't matter, same result. So yeah, that gives you the same answer. Which one was quicker? The first one was still quicker. Oh. It was supposed to be. OK. Now, of course, this is the simple version. We didn't have much difficulty. So I'm just going to do the same question over with a little bit of a difference. Well, two little bits of difference. OK, that's all of it. So this time, I'm still going to have this mass sitting here, connected with a string. This time, the other mass is not going to hang directly down. It's going to be sitting on an inclined plane there, and which makes an angle theta with the horizontal. And now I'm going to have friction on both surfaces between the blocks and the surface. Now again, we'll try to solve A for the acceleration and B for the tension in the string. Now, which way to do it? Free body diagrams? All right. So I'll do it once. You can try the inspection thing. I'll do the free body diagram solution. Now, for this mass, free body diagram. So I have mg acting down, normal force acting up, tension in the wire pulling to the right, and the force of friction pulling to the left. OK? I get two equations. So I have, well, it's going to accelerate to the right, which means T minus the force of friction equals ma, and n equals, no, I say n minus mg equals 0. And of course, I get n equals mg, and the force of friction, wait a minute, this is not little m, is mg mu, and I get T minus mg mu equals capital M times A. The same equation as last time, because that part of the problem didn't change anyway. Now, for the second mass, it's sitting on an incline. I need to get two equations out of this. So I need two independent directions to be happy. What coordinate system should I choose? The one that's parallel to the surface gives me an easier time. So I'm going to choose my positive x as that. And I'll call them x prime and y prime, just in case you were thinking of these as x and y. And I'm going to write my equations in those directions. Let me just draw the forces that are acting on it. Well, in this direction, I have mg. In that direction, I have n. What else do I have? Tension. Sideways T. and I have friction, right? The friction force, and that's pretty much it, right? So the first equation I will write in the x prime direction, choosing this as positive, and well, of course, the overall acceleration is going to be in the x prime direction that way. So the force, of course, I'll have to split this mg into its components along the axes that I chose. So this one is going to be what? Mg cosine theta. This is going to be mg cosine theta. And in this direction, this one is going to be mg sine theta. I didn't mix them up, did I? No, good. OK, so I'm ready to write my equation in that direction. So it is, no, I did mix it up. Yes, yes. I was worried about that. So why was I worried? OK, so how did I figure I got it wrong? When theta is 0, right. When theta is 0, it's not supposed to go downhill. With a cosine, you get mg, which doesn't make any sense. It's flat. When it's flat, it needs to be 0. So this one is mg sine theta, and this one is mg cosine theta. Now we're happy. Good. So forces in this direction, mg sine theta, positive. Tension acting the other way. Force of friction acting the other way. And that's it. Equals little m times the acceleration, net force.
Force of friction number 2.
Force of friction number 2, right. Not to mix it with the symbol here. Well, my force of friction symbol does not leave this part, so it wouldn't have mattered, but yes, being explicit is good. Explicit is better than implicit. The other direction, I have positive normal force, negative direction mg cosine theta equals 0, because we're assuming it doesn't go into the inclined plane. So the normal force is mg cosine theta. Therefore, the force of friction number 2 is mg cosine theta times mu2. And over here, I should have said mu1, right? Mu1, fixed. All right, then the equation here is mg sine theta minus t minus mg cosine theta mu2 equals mass times acceleration. Equation number 1. Equation number 2. I have T and A should be doable. Usually if you have a single tension, the same trick will work. Adding the equations side by side always cancels that. So you get, if I put that over here, so I have T minus capital Mg mu1 equals mass times acceleration. Add them together. So T's cancel. What do I get? Mg sine theta minus mg cos theta mu2 minus capital Mg mu1 equals little m plus capital M times A. Thus, if I manage to pull the acceleration out of that, I get what? Everything comes with a g. So on the top, I have m sine theta minus m cosine theta mu 2 minus capital M mu 1 over capital M plus little m. Okay, well, that gave you the acceleration. I'll have to erase the free body diagrams. Once I have the acceleration, I can use again either equation to get to the tension. I'll use this one. In this case, this one is simpler. So the tension is m times a plus capital M times g mu 1, which is equal to mg mu 1 plus capital M times g times this whole animal here. Mu 2 minus capital M mu 1 over m plus m, which is capital Mg parentheses. I have mu 1 capital M, mu 1 capital M plus mu 1 little m plus m sine theta minus m cosine theta mu 2 minus capital M mu 1 over m plus m. There is going to be 1 cancellation. And that's about it, right? Nothing else cancels. So I get tension is mg mu 1 m plus m sine theta minus little m cosine theta mu 2 over capital M plus little m.
You can put everything in small and parentheses.
Right, okay. So I can do that. That becomes funny like that. Now, does that make sense? To you, it doesn't make sense. So I have a positive sine theta there. That makes sense because as theta grows, you have more of an incline, so you have more tension. I have mu 1 is positive, so the more you hold this guy back, you get more tension in the wire. And I have a cosine theta mu 2 as negative. Because the more friction you have here, the less you'll be pulling it down with less force. So I think it makes sense. Are the units okay? Well, here again, g is an acceleration. I have mass over mass. I'm happy. Here, well, this part is unitless. There's a mass in the bottom. If it cancels one of the masses, so you have an mg, which is a force. So I'm still good. Yeah, that's the solution of the problem.